So first slide is just a little bit about me. This is me. My name is Evan Simmers. I'm 27 years old, and my current title is Analysis Lead at Rocket Lab. For those of you who haven't heard of Rocket Lab before, we're a New Zealand-based company. We build launch vehicles, so we build rockets that go to space, and those rockets deliver satellites from customers all over the world, from here in New Zealand, from over in Australia, the US, Europe, in order to do really critical science missions. So looking at things like tracking weather, looking at near-Earth observation, doing basic science missions in space. Really kind of contributing to the space ecosystem. My other role at the company is I'm the mechanical lead for our space systems team. And one of the missions that we're doing in our space systems team is we're going to the moon. So that's what we're going to be talking about today. In my undergraduate degree, I studied mechanical engineering, and we'll be talking about that a little bit as well. Cool. So my career story, I started out in high school. So this was my high school, Onslow College. And I was really interested in maths and science, as you can imagine. So I studied calculus, statistics, and physics, but I also did kind of some other things too. I did some English and some classical studies. And then moving into university, I completed a Bachelor's of Engineering in Mechanical Engineering, and I completed a Bachelor of Arts in Philosophy and History. And while I was doing that Bachelor of Arts, I had the opportunity to go over to London for a year to study at University College London, which was a great experience. And then immediately after coming back and finishing my degree at the University of Auckland, I joined Rocket Lab. So I joined Rocket Lab as a junior analyst, and then across the last 4 years have been kind of building my own personal capability and my integration with the company, and I'm now leading a group of 8 engineers directly and a group of probably 30 engineers as a cross-functional team. Who are working together to solve this problem of getting to the moon. Cool. So if we look at what is engineering and what is mechanical engineering, I classify engineering as team-based problem solving with maths and science. This is personally the thing that gets me most excited about engineering. It's working together on ambiguous problems and solving them as a team. And so that's engineering in general. And then if we look in a little bit more detail about what mechanical engineering is specifically, I like to classify mechanical engineering as building stuff that moves. So that could be a car, that could be a plane. People don't really think about moving parts in skyscrapers or in infrastructure projects, but there's a lot of fluids. So there's a lot of water, air, gas that you need to move around a building efficiently and effectively. So that's a big part of mechanical engineering. It could be planes, it could be trains, and in my case, it's launch vehicles. So it's rockets. Cool. But this is what we're here today to talk about, which is how to get to the moon. And just to add a little bit of flavour to this, Rocket Lab recently signed at the start of this year a project called Project Capstone. Project Capstone is working with NASA in order to provide the precursor mission, or the kind of pathfinding mission for the Artemis program. Artemis program is the program that's sending humans back to the moon. So it's a super exciting program to be a part of. We're going to be the first mission in the Artemis program, and the purpose of the satellite that we're flying to the moon is to have confidence in the lunar gateway, it's called, or there's going to be a lunar base that orbits the moon, and we're going to be sending the first satellite into the same orbit as that lunar gateway in order to ensure that orbit, so that the path that lunar gateway will take as it orbits the moon is a path that doesn't have many disturbances and is a safe place for people to be. The purpose of that lunar gateway is that we can send people to that gateway, and then they can, from there, traverse down to the moon, and then they can spend, rather than spending hours on the moon, so for the Apollo program. So those of you who have heard about us going to the moon back in the 60s, that was kind of 24 to 48 hours you'd get to spend on the lunar surface before you had to come back. As a precursor to getting to Mars, we really need to be able to be practicing missions that are week-long in duration, trending into kind of month-long in duration. So the Lunar Gateway allows that to occur, and it's been really exciting and very personally enriching project to be a part of as we work our way towards the moon. Cool. So now we'll jump into the things that you need to get to the moon, and the first is a great team of people. It takes a lot of people to launch a rocket, and I'm very humbled to be joined with some really phenomenally intelligent and hardworking women and men in the Rocket Lab team who have contributed to the Capstone program. We can see this is a photo from a couple of years ago, but we've got engineers across a range of disciplines that it takes to build a rocket. You've got engineers like myself, mechanical engineers, software engineers, avionics or electrical engineers, propulsion engineers, which are kind of similar mechanical engineering but a specific sub-focus. And then there's a host of other technical disciplines that aren't necessarily engineering. So there's a lot of technicians. So if you like working with your hands, engineers typically work with computers. If you'd like to work with your hand and actually be physically building rockets, you'd be a technician, whether that's a vehicle technician who are dealing with metallic assemblies, so pressure vessels, or if you're a composite technician, our rocket's made out of carbon fiber. You can see a couple of the rockets in the background of this photo. We've got some of the best composite technicians or composite builders in the world. A lot of them come from either an automotive or a naval background. We do some of the best carbon fiber yachts in the world here in New Zealand, and we've been fortunate enough to draw on that experience and that knowledge as we've been building Electron, which is our rocket. But yeah, a big part of building a rocket is building a team, and we're very lucky to have such a strong team here at Rocket Lab. Cool. So the next thing you need, obviously, is a rocket. So this is our baby. This is the Electron launch vehicle. The Electron rocket is special for a couple of different reasons. The first I mentioned before, we've got a carbon fiber reinforced plastic fuselage, which is kind of the external skin of the rocket, and which provides most of its structure. Carbon fiber is really light, and it's also a meta material. So it's a material which you can determine the properties of the material as you build the part, which is something that adds a level of complexity to the design process, but is something that's really exciting if you're trying to build these really highly optimized structures that you're willing to spend a little bit more time designing and a little bit more money buying in order for them to be lightweight for how strong they are or how stiff they are. Another really important part of the Electron launch vehicle, you can see the fire coming out the bottom, and if you can see, I'll try and put my cursor over it. We've got these little sections here. These are the engines of our rocket. So that this is we fly a Rutherford engine. There's 9 on the first stage. So there's 3 stages to the Electron launch vehicle. We jettison those stages as we ascend into the atmosphere, because once we've depleted or once we've drained all of the fuel in our rocket, we don't want to be carrying the dry mass of the tank from that fuel with us all the way to orbit. We'd prefer to throw that away. And the Rutherford engines are the world's first electric turbo pump engine. So in order to get the fuel into our rocket engine, we need to pump that fuel into that engine, and all previous rocket companies have done that with a gas generator cycle, which is kind of similar to, not dissimilar to a aircraft, an airplane jet engine, but we use an electric turbo pump, so we use an electric engine, which has a range of benefits. Kind of turns a hardware problem into a software problem, gives us some really precise timing, and it also allows us to leverage the continuing improvements in battery technology that have occurred as a function of the consumer electronics market. So that there's a lot of people thinking really carefully about how we can make batteries better so that your phone can last longer or your laptop can last longer. and we get to leverage the improvements in capacity and performance of those cells to make our rocket better over time, which is a really key strategic advantage for the company. Cool. Once we've got our rocket, the next thing we need is a satellite. So this is the Capstone spacecraft we can see in gold on the left-hand side here, and this has been a big chunk of my year this year as we've been building towards the build of this spacecraft. So as a mechanical engineer and as mechanical lead of this system, I'm responsible for all of the physical stuff you can see. So there's a bunch of stuff here that's not hardware. So there's some computer boxes that we call them avionics boxes. There's some solar panels you can see here. This is a solar panel. You can see this gold foil. This is actually kind of very similar to aluminium foil that you'd have at home if you were roasting a lamb or something, but it's got a special coating on the outside of it that makes it suitable for space. So that's all dealt with by other people, but the general structure here, this pressurant bottle, these are propellant tanks in here. This main structure, these are all elements of the mechanical system that we are developing to get us to the moon. Probably another important caveat is the thing that we're sending to the moon, we call a payload. You can see in the top of this image on the right-hand side, this is our payload. So we will be custodians of this payload across the mission duration. So the mission is the length of time needed to get this satellite to the moon, this payload to the moon, but our satellite is not the payload. So our satellite has a thruster, so it can go places. It's got some reaction wheels, so it can make sure that it is pointing in the correct direction. It's got some solar panels to make sure that it's powered, and it's got some thermal control to make sure it doesn't get too hot or too cold. But the actual science that we're going to be doing, so the data that we're going to be sending back to Earth is the responsibility of the customer, and it's mounted up on the top of the payload. We can see this gold edge and this black background. Great, and then the final point technically in the talk is how is how we're actually going to fly this thing to the moon. So we can see a rough diagram here of how we get this satellite from Earth to the moon. And when we're one of the really interesting and kind of non-intuitive aspects of this this problem is that we don't just fly directly to the moon. So step one, we start on the ground in New Zealand or in the US. We still get to determine where we're going to be launching from. And then we'll fire up our first stage. So that's the stage of the rocket with the 9 Rutherford engines. We'll then get to a point, we'll jettison that first stage, and we'll start our second stage burn. So that's a smaller portion of the rocket with a single Rutherford engine. And then once we get up to point 3, we're going to have a secondary burn of the third stage of our vehicle. And we're going to circularize our orbit, and we're going to be in a circular orbit around the Earth. And then this is when things get exciting because over the next few days, once we've checked out our systems and made sure that everything is working correctly in the circular orbit, we're going to successively raise what's called our apogee, or the kind of the furthest point away from the Earth, through a number of burns that you can see, kind of 4 and 5. We're going to continue these apogee raising burns. This gives us it's kind of similar to a slingshot, or if people have ever done a hammer throw or a discus, we're slowly building up the kinetic energy in our system before we make the shot to go to the moon. And then when we get to 5 here and 6, these are successive burns that we do. These are our translunar injection burns. They're the most important part of the whole mission because we're going to be pointing at something a long way away. We've got to make sure that we're very accurate in the way that we point, and we burn do our final burn to give us more kinetic energy to get us to the moon. It's also important that we're moving in space and the moon is moving as well with respect to us. So it's not like we just point at the moon to get there. We need to point at a position in front of the moon so that when we get there over the course of many months, we will intercept the moon in an orbit that is stable. And that's what there's a few additional elements, 8, 9, and 10, but that's kind of the basic idea. We start in a circular orbit, we raise our apogee, and then we have a translunar injection burn. Great. So I thought at the end of the talk I'd touch on briefly some of the key skills that I brought out of both my high school and undergraduate degrees that have allowed me to be successful in my current role, and some of the really key parts that maybe you wouldn't expect if you were at high school. So problem solving is a really, really critically important part of my my day-to-day work. It's something that every single day I come in and am engaged in solving a different type of problem with a group of people, which I find really exciting. I need to do a lot of data analysis for my role. So that's whether it's in Excel, you guys probably have a little bit of experience in Excel, or in different code platforms to be able to interpret data and then to gain insights from that data that allow us to make decisions about the rocket. And then really important, I need to also be able to clearly communicate the outputs of that data analysis or that problem solving to a wide group of, we call them stakeholders, but just people who are interested in the project that I'm currently working on. It's definitely not enough to just do the technical work. You also have to clearly communicate the outputs of that technical work, or the conclusions, so that everyone is aware and everyone can work together. It takes a really big, wide group of people with a range of different skills to build a rocket. So they may not understand the really detailed technical work that you're completing, but you need to be able to communicate the overall vision of that work to them so that they can work in harmony with your skill sets, and then they can do the same for you because you won't understand their direct technical skills. Great. And then one thing that I do at your age before pursuing a STEM career is that I enjoyed maths and science, and engineering was a pathway in order to make those skill sets manifest in the world. I also really like the idea of being able to touch something and say that I built something, and I contributed to this project that's helped people's lives. But engineering is really about people. The only reason that we build a bridge or we build a train or a plane or a car is to benefit and make people's lives better. And it's really important to keep that in the forefront of your mind as if you're looking to pursue a STEM-based career. The things that we do in the technical problems that we're only solving those problems because they make people's lives better. Great. I think that's the end of my talk, but I'm happy to field any questions if you guys have any questions.
Participants, if you've got a question you'd like to ask, please feel free to write it in the Q&A box in the ribbon at the bottom of your screen, and we'll get Evan to answer it. If you've got something, pop it in there quickly now.
Just while we're waiting, there's a question from the Wonder Project. Evan, would you like to walk on the moon one day?
Yeah, no, I'd love to. I think it'd be very exciting. It's the moon's quite far away. It takes a while to get there, and it would take a while to develop the. You need to have a lot of training in order to be able to perform that role. But I think that'd be super exciting. I'm not quite sure about Mars. Mars is quite far away.
Yeah.
And you need to stay on Mars for quite a long time. If you want to go to Mars, you need to go for kind of a minimum of 2 years. I'm not sure if my partner would allow me to leave for 2 years, but I'd definitely like to go to the moon.
Awesome. No, there's a question there for you, Evan. Tim asks, he wonders how big the satellite is that you described.
Oh, that's a great question. Our satellite is roughly 1 meter in diameter. It's a cylinder, and it's roughly 600 millimeters, so 0.6 meters in height. So that's probably, if you imagine a coffee table or like a small fridge, maybe an oven, that kind of size. The 4 tanks of propellant that we have on board the vehicle are 50 liters each. And our thruster, so the engine at the bottom of the vehicle, is probably I don't know, maybe 50 centimeters tall. So it's the kind of things you can pick up with your hands and manipulate. So they're not huge, but they still need to be really highly performant. So they need to be very light, because it's rockets are fundamentally turning chemical energy into kinetic energy. And for those of you who have done some level 1 or level 2 physics, a big part of the kinetic energy term is that mass term. So reducing the mass as much as possible means that you can go as fast. You can go faster for the same amount of energy.
And we've got one more question. Charlie wonders how fast the rocket and satellite moves.
Yeah, another great question. It's super fast. So as you continue through different phases of the mission, you're going faster and faster and faster. The satellite itself will have a terminal velocity of about 7 kilometers per second. Yeah, which is wicked fast. It's for those of you who to put that in perspective, a plane, if you're flying from New Zealand to America or New Zealand to the UK, your plane, you're probably flying in an Airbus or a Boeing. That'll be going at about Mach 0.7, so 70% of the speed of sound. 7 kilometers per second is about 25 times the speed of sound. So you're going more than 25 times faster, probably 30 times faster than the fastest that you've ever gone as a person if you've flown in a big plane.